So as you're probably aware, the area of a circle can be found by taking the radius and squaring it, multiplying it by pi, and we can prove this using calculus. What I'd like to do is consider what about a just slice of the circle, a pie piece or a pizza slice. So now we're only going to take theta of that particular circle, and I'll move this r here so it's easier to see. So we're taking just a portion of the circle. What would that area be? Well, basically we're just taking a fraction of the whole area. So we don't want the entire circle, we want a piece of the circle. So what fraction of that circle are we considering? Well, we have theta for our angle, and the total angle, if we were to take the entire circle, that would be 2 pi. So this is the fraction of the circle that we want. For our circle sector. So I can simply take this fraction and multiply it, stick it right there in my area formula, and that gets me the area of that fraction of the circle. But you notice, of course, that the pi's here cancel, and so a simplified version might be 1/2 r squared theta. And that's a pretty good formula for the area of a circle sector. Given theta needs to be given in radians, of course, because, well, we expressed our fraction in terms of radians. Okay, so why does this help us? Well, if we want to find the area of a curve defined with polar coordinates, we're going to need to use circle sectors. So let's take a look at what that might look like. So now we're in the xy plane, and I'm going to take a curve defined by a polar equation. Here it is right here. The r is given by some function r of theta, and I want to know what the area is between that curve and the origin given by a couple of theta values. Let's say this is theta is equal to alpha, this is theta is equal to beta. And so I want to know, what is this area right there? So one thing I can do is I can split this up into a Riemann sum. So what does that mean? That means I'm basically splitting it up into tiny little chunks. So let's take a look at one of those little chunks right here. So there's a particular theta, and what I'm going to do is I'm going to add a little bit of thickness to it, and we're going to assume that this thickness is given by the angle delta theta. So let's say that this is the theta, and then this is the theta plus a little delta theta. And we're going to assume that this is a circle sector, like this piece up here. So what's the area of this little piece? We can call this a delta area. So this little tan thing here is a piece of the entire area, delta A, for part of the area. And we can use the circle formula, because the circle sector formula, because we can figure out the radius. The radius is going to be given by r of theta, so we'll square that. And the angle, we said, was delta theta. And that's just one piece of the area, and so we'll do our normal trick to build up the entire area with all these little pieces. So you do this for all of them until you fill out the entire area. And so you're going to add up all the little delta areas. And what do you get? Well, you're going to add up a bunch of little angles, delta theta. And this is exactly the setup for a Riemann sum, which is how we define a definite integral. And so ignoring some particulars of how this is actually done, the idea is that your sum becomes the integral sign, your delta theta becomes the differential d theta. Now it's an infinitely thin angle, and everything else, I forgot the square here, everything else comes on down. 1/2 r of theta squared, and then since we're adding up these little angles here, We're just going to take the angle from the starting angle alpha to the ending angle beta. And that's going to be my entire area. Okay, so there's the formula right here. We can factor out that 1/2 if it helps, and I'll write it in black as well. So the formula that we often will use has that 1/2 factored out. Integral from alpha to beta, r of theta squared d theta. Okay, so there's our formula. And this will allow us to compute the area between a polar curve and the origin. Okay, so let's take a look at an example of this. Find the area bounded by a cardioid, r equals 2 plus 2 sine of theta. All right, so first things first, it helps me certainly when doing these problems to draw a picture of what's going on. So let's go ahead and sketch this. I'm going to plot a bunch of the theta values. I'll do the usuals, 0, pi over 2, pi, 3 pi over 2, and then 2 pi is going to be the same thing as 0, of course, because it's defined in terms of trig. So 0 is going to give me 2 plus 0, and that'll be the same as 2 pi. When I plug in pi over 2, that's 2 plus 2 is 4. If I plug in pi, I get 2 again. If I plug in 3 pi over 2, I get 2 minus 2 is 0. And you can check my work on that if you like. But let's go ahead and plot those points. When theta is equal to 0, I get 0, I go out 2 for the radius. When theta is equal to pi over 2, I'm going to go out 1, 2, 3, 4 for my radius. And theta is equal to pi, I'm going to go out 2. When theta is equal to 3 pi over 2, I'm going to go out 0. So let's draw this. And it's going from 2 down to nothing, and then it goes from nothing back out to 2. So there's our rough sketch of how this shape works. We're looking for this area right here. And the important thing that this sketch tells me is that this area does go exactly once all the way around from theta is equal to 0 all the way around to theta is equal to 2 pi, which means that the area formula that I want to use should run from 0 to 2 pi. Area equals 1/2, 0 to 2 pi, and we're going to square the radius, r of theta. Now in this question, r of theta is 2 plus 2 sine of theta. 2 plus 2 sine of theta. Yep, that'll do it. So let's square it out. 4 plus 8 sine of theta plus 4 sine squared of theta. No way I can integrate the sine squared as it is. I'm about to use the double angle identity. So let's recall that sine squared of theta is 1/2 minus 1/2 cosine squared of theta. Sorry, cosine of 2 theta. So let's plug that in. I can multiply both sides by 4. 4 sine squared of theta is 2 minus 2 cosine of 2 theta. There we go. Plug that in. So the 4 sine of theta, sine squared theta becomes 2 minus 2 cosine of 2 theta. Combine the 4 and the 2. Actually, I can also multiply in that 1/2. So algebra, what do I get? I get 4 plus 2 is 6, divided by 1/2 is 3, plus 8 divided by 2 is 4 sine of theta. 2 divided by 2 is cosine of 2 theta. All right. Finally, something I can integrate. This integrates into 3 theta. Let's see here. Minus 4 cosine of theta minus sine of 2 theta but I need a 1/2. And I could do substitution to figure that out, but honestly, I just think about this going backwards. Sine of 2 theta, I know it has to involve that. Sine becomes cosine. A 2 pops out, cancels with the 1/2 to get a 1 cosine of 2 theta back there. All right, plug her in. Plug in the top, I get 3 times 2 pi minus 4 cosine of 2 pi minus 1/2 sine of 4 pi, all that minus plug in zeros, 0 minus 4 cosine of 0 minus 1/2 sine of 0. And this is one of those cases where you need to remember, don't ignore the 0 because not everything zeroes out. This is a 0, that's 0, but cosine of 0 is 1. So I've got minus a -4 here, so I got a plus 4 on the right. Here on the left, I've got a 6 pi minus cosine of pi over 2 is 1, so minus 4. And then I have a minus 1/2 sine of, that is a big fat 0 there. So it looks like my -4 and my +4 cancel. So I'm left with 6 pi for my area there. Okay, now let's take a look at one more example here. But before I do that, let me point out something. What if I wanted to find the area between curves, just like we do for Cartesian coordinates? And in this case, the two curves, because we're dealing with polar, the two curves would look something like this. You've got an outside curve, and I'll call this big R of theta, and we'll have an inside curve, which we'll call little r of theta. All right, and I want to know the area between these two curves for particular theta values, which it might be where the curves cross each other, or I might be told what the theta values are, but here's theta is equal to beta, theta is equal to alpha. And remember, we think of this as going counterclockwise from the smaller alpha to the bigger beta. So I'm looking for this area right here. Well, all I have to do is think of it as I want the whole area. That would be all of this area, but I want to subtract away the area inside the purple. And if I take the purple away from the blue, I'm left with that green that I had there. Okay, well, that's easy enough because it's just a matter of subtracting one area from another. The area would be the big area, alpha to beta, 1/2 big R of theta squared minus the small area, 1/2 alpha to beta, little r of theta squared. But of course, we've got the 1/2s, we've got the same boundaries. The formula that we'll often use is just alpha to beta, big R squared minus little r squared d theta. Outside, inside. Outside curve, inside curve. And then the alpha and the alpha is the clockwise angle, beta is the counterclockwise angle. And so this is kind of a more powerful formula that allows us to talk about basically any type of area described in polar coordinates we can model like this, at least the ones that we're interested in. So let's take a look at a particular example. All right, there it is. We're going to find the area inside of a circle, but outside a cardioid. So let's see how that would go down. I think I definitely want to take a picture, sketch a picture of what this looks like. So let's see here. So I know what the circle looks like, that's easy. I don't know which one's going to be inside or outside. Actually, I do know which one's going to be inside and outside because we want our curve to be outside the circle, which means that the circle is going to be inside curve. So I want the area to be outside of it. So here's our circle of radius 1, easy enough. All right, that's going to be inside the cardioid. 1 minus cosine of theta. And to sketch this, that'll be my outside curve. I really need my chart here. So theta is 0. I'm going to get 1 minus 1 is 0. Pi over 2, 1 minus 0. Pi would be 1 minus a negative 1. 3 pi over 2 is back to 1. 2 pi is the same as 0. So let's plot those. At angle 0, 0. At pi over 2, 1. Looks like this. At pi, we go out 2. And then 3 pi over 2, back down to 1. And then back to 0. So again, we want to be inside the cardioid, so this is going to be our outside curve, but we need to be outside the circle. So we have to be outside the circle, but inside the cardioid. So it looks like this is the area that I'm looking for here. That's the area that's both inside the blue curve, but outside the purple curve. Now, since that's our area, we're going to be able to figure out what our theta value should be, because the first point is that theta is equal to pi over 2. And our last point, if we go around counterclockwise, our final point is at 3 pi over 2. So that's my beta, and that's my alpha. Okay, now it's just a matter of using the formula. Area is equal to 1/2 alpha to beta, big R squared minus little r squared. Okie doke, what would those be? 1/2 alpha is pi over 2, beta is 3 pi over 2. Oh, what are my big R and my little r? Okay, well, let's go back to the problem. First of all, let's just label those with colors. My outside curve is the big R. So the big R is the blue curve here. That's on the outside. And it looks like I've already told what little r is going to be. It's going to be 1 minus cosine of theta squared minus the little r. I was not given as a polar equation, was I? Let's see, that little r, the inside of the region that I care about here is in purple, and it was given to me in Cartesian, but that's okay because the circle equation is the easiest one of all to come up with in terms of polar. It's a circle of radius 1, so that's just going to be r is equal to 1 squared d theta. Can't forget that or I won't know what to integrate with respect to. So now I'll just do some trig and algebra. So square this out, I get 1 minus 2 cosine plus cosine squared minus a 1. So the 1's cancel here and here, d theta. 1/2 pi over 2, 3 pi over 2. I got to split up this cosine squared. That's 1/2 plus 1/2 cosine of 2 theta. So I have negative 2 cosine of theta plus 1/2 plus 1/2 cosine of 2 theta. And if you want, you could multiply in that 1/2. So I get negative cosine of theta plus 1/4 plus 1/4 cosine of 2 theta. Okay, now I integrate and I get negative sine of theta, 1/4 theta, and let's think about this for a second. It's going to be 1/8 sine of 2 theta, because that 2 will pop out, cancel with the 8 to get 1/4. That's from pi over 2 to 3 pi over 2. I'll plug in top minus the bottom. Plug in the top. Let's go ahead and write it all out. Let's see, it's going to be 3 pi when we multiply that by 2. Negative sine of pi over 2. 1/4 pi over 2. 1/8 sine of pi over 2 times 2 is just pi. Okay, sine of pi, sine of 3 pi, they're the same thing. They're both nothing. Get rid of those. Sine of pi over 2 is 1. Sine of 3 pi over 2 is -1. So I'm getting, let's see, +1 plus, looks like 3 pi over 8 minus -1 pi over 8. All right, so I've got 1 minus, let's go ahead and multiply out that negative. So 1 plus 3 pi over 8 plus 1 minus pi over 8. So it looks like the final answer is going to be 2 plus 2 pi over 8, 2 plus pi over 4. And that is the area. It's a positive number, so that does seem reasonable to be the area of that particular region that we drew way back over here.